Mathematical optimization provides us with tools to tackle large classes of optimization problems. My main research interest is in using these techniques and applying them to specific problems with real-world applications. Hello, I'm Bart Smeulders. This is a short introduction to my research. The study of combinatorial optimization usually starts with traditional problems such as matching and routing, with some very good reasons. These problems are easy to state, teach us a lot about optimization techniques, and they're also easy to motivate. We can easily imagine them being used in practice. However, once we go to applications, there are usually some complications. This is my favorite application, kidney exchange. The idea is fairly simple. We have a bunch of patients who are in need of a kidney. We also have donors who are willing to donate their kidney to one of these patients. But the patients and donors are paired. A donor in a pair is only willing to donate if the patient in the same pair receives a kidney as well. And the donor in the pair usually cannot donate to the patient directly. Now we need to find a solution where we have as many transplants as possible, satisfying this restriction. And we can solve this fairly easily with a perfect matching problem. In this figure, the pairs are shown with dashed lines, and the full lines show which patients and donors are compatible for a transplant. We now want to find a solution where every patient and donor is linked to a patient or a donor, and we have as many of these full edges as possible. This is a well-studied problem, and we can solve it fairly easily. In practice, kidney exchange is more complicated. One reason for this is the uncertainty of compatibility. It very often happens that a perfect matching is found, and medical tests afterwards show that some patient or donor who are scheduled to be transplanted are not compatible after all. Preferably, we'd like to do these tests beforehand, but this is very expensive, both in time and money, to test all possible patient-donor combinations. So in one application, we studied the problem where we wanted to find a small set of edges to test, such that the expected number of transplants after a test was as large as possible. This is a challenging optimization problem requiring techniques from stochastic programming and decomposition techniques to which we needed to add some insights into the specific problem. A second complication for kidney exchange could be competing interests of participants. Usually there are multiple hospitals or countries involved, and they all have their slightly different preferences to have their own patients preferred. In this example, we could have two different solutions. One where both of the red pairs are matched together, or the best overall solution that has 3 transplants where pairs 2, 3, and 4 each exchange. To handle this complication that red would not like the second solution, we studied a problem where we looked at a solution with as many transplants as possible under the restriction that every participant could potentially veto certain exchanges where their pairs were involved. This led to a bi-level optimization problem for which we needed to use techniques from this area, and we also improved these somewhat for integer programming games. I hope that these examples show that to do applied combinatorial optimization, you need to have a broad knowledge of different optimization techniques, because different applications will require you to make use of these. On the flip side, insights from specific applications can help us inform development of more general techniques. So where is my focus exactly? On the technical side, I mostly study problems with multiple decision makers. They can be settings where there are slight differences in preferences, such as in the kidney exchange, but we could also have situations where the different participants are really adversarial. From the application side, I work a lot with healthcare applications, kidney exchange, but also with Eurotransplant, where we have a collaboration to study and further develop their organ allocation mechanisms for deceased donors. A second application area are security settings, where we need to assign resources in such a way that we can prevent attacks from a strategically thinking attacker. This research is in collaboration with Dutch security services. So, I hope this gave you some idea about my research. If I have to sum it up in one line, it is a quote that was originally about statistics, but I think works very well for our research area. The nice thing about applied optimization is you get to play in everyone else's backyard. And this is what we do with these many applications.